And welcome to the 8th video in the Learn Machine Learning series. And today's video, we're going to be talking about random forest models and k-nearest neighbors classifiers. So today's video is about completely finishing off the machine learning series. There are 10 videos in the series, the 8th one, and today is probably going to be our last lecture on classifiers. And today we'll talk about two really crucial classifiers in the machine learning world, random forest models and k-nearest neighbors. And both are relatively easy to understand. So let's get into it, and hopefully you enjoyed the video. Make sure to drop a like and subscribe. Let's get started. Let's first talk about random forest classifiers in order to introduce the topics in this video. What is a random forest classifier? You can really think of a random forest classifier as a group of decision trees. I think that's a really good analogy because the name forest, well, in real life, a forest is just a group of trees, right? A bunch of trees. So similarly, in machine learning, a random forest classifier is really just a classifier where the main structures is just a bunch of decision trees. And in more technical terms, it's an ensemble method or divide and conquer technique of decision trees, right? It's a bunch of decision trees where it's a divide and conquer method to create the decision trees, and then we have multiple decision trees and we iterate through each decision tree to get a vote. So let me explain what I mean. If we have some kind of data set or some problem, we have a certain number of samples or maybe training examples in that problem. So what we could do is that we could split our data set, or X data set, into a certain number of features. Feature N1, feature N2, feature N3, N4, and etc. And so since we split our X data set into a bunch of features or inputs, we can then create an individual decision tree for each feature or input. And for each decision tree, we basically attain some kind of output. So as you can see in this graphic, you can see that in tree 1 we get class C, tree 2 we get class D, tree 3 we get class B, tree 4 we get class C. So we take all the votes or the class of each decision tree and we total it up. So we say how many times was class C voted for, how many times was class D voted for, how many times was class B voted for, etc. And we see which class has the most votes, which class received the majority votes from the decision trees as a whole, and that class with the most votes, or the mode of the class of all decision trees, is the final output prediction class. So it's a pretty simple method. It's just that we have a number of features. We make a decision tree for each feature. Each decision tree is going to spit out a certain class or output. We sum all the outputs from all the decision trees. We take the most common output, the mode of all the classes, and that's our final prediction. So as you can see, random forest is a really intuitive classifier. It makes a lot of sense on both the practical basis and in terms of the theory. So let's just review how it works. So, like I said earlier, we construct several decision trees, and we output the most common class after the votes of all the trees is summed up. And this is pretty easy to understand, right? So the same exact thing as last time. We have a data set, we break it down to features, we make a decision tree for each feature, and then the decision tree is going to give us the output based on the feature. So as you can see, N1 gives us class N, N2 gives us class O, N3 gives us class M, N4 gives us class N. We see the most commonly occurring output from the decision trees, or the mode of all the outputs, aka the most common output, the one with the most votes, right, from the most decision trees. In this case, that's class N, right? And then we output that as our final class, or final prediction, or final output. So there you go, that's how decision trees work. How do we actually construct a random forest classifier? So there's a 4-step process. So step 1, we want to select a random sample from a data set. So what I mean when I say select a random sample from a data set is that we basically want to take, going back here, we want to take our data set and we want to take a random sample of the features in that data set. Not the labels, not the classes, but the features, right? There are inputs in the data set. We want to take a random sample of those inputs. Step 2, for each sample or each input or each feature, we construct a decision tree. And out of the decision tree, just like I think we talked about decision trees in video 3 or 4, decision trees are like Boolean structures, right? Basically if-then, and it's a bunch of if-then Boolean trees, right? Subtrees, there's leaf nodes, etc. And so each sample or feature or input is going to have a decision tree. And then we basically take the sample, run its information through the decision tree, and based on that we get an output, which is our prediction result, which is some class, right? So going back here, that's where we get class N, class O, etc. Step 3, we perform voting, right? This is where we basically look at all of our decision trees, which could be thousands of decision trees, and we sum up the votes. How many votes for each class were there, right? So let's just say we have 1,000 decision trees, and 50 decision trees gave us the output for class M. So there you go, the vote for class M is 50 votes. Let's just say for class O, we have an out of 1,000 decision trees, 700 voted for class O. 700 output is class O. Then our vote for class O will be 700. So that makes sense, right? And then the final step is that we want to see which decision tree actually does have the most votes after we perform voting, and that's what we finally output. That's the very last step in the model. That's what we can output as our final output. So there you go. That's how a decision tree works, and I think it's a relatively simple classifier. So let's just talk about some of the more interesting features of a random forest classifier, some of the advantages and disadvantages. What are some advantages of the random forest classifier? Well, it's highly accurate and robust due to the fact that there's multiple decision trees, right? So going back to much earlier in the series, we talked about how decision trees itself are really useful classifiers. Well, in this case, we have so many decision trees, one for each input or feature, right? So this is a very accurate and robust algorithm. You're going to get very high performance, and it's going to be robust in that it adapts really well to training and test data. Another advantage of random forest classifiers is that it's less likely to overfit. Once again, since we have multiple decision trees, this cancels out bias. Since we're getting a major screening of all across so many different decision trees that bias is not even possible, right? Just think about it. In a problem where there are 100 input features, we make a decision tree for each input feature. Therefore, we eliminate bias from each of those features because it's a Boolean decision tree process, right? So this algorithm is much less likely to overfit, which is a good thing, right? And another advantage is that it's a very versatile algorithm. It's useful for both regression and classification, and even search problems. So there you go. Those are the advantages of random forest classifiers. What are some of the disadvantages? Well, some of the disadvantages of random forest models or classifiers is that it's a little bit slow and inefficient in prediction generation. Why is it slow and inefficient in prediction generation? Well, it's because as you scale up with more data, as you exponentially increase the amount of data and features, you have to generate a decision tree for each input feature. And this can take a lot of time for an extremely large amount of features, right? So therefore, it can be slow and inefficient when you scale up to larger data. Also, it's harder to visually interpret compared to decision trees, right? Like a normal decision tree, you can usually branch it out into the different subtrees, the different leaf nodes, etc. However, for a random forest classifier, there's a bunch of decision trees, right? So it's really hard to understand how each one works, and each one has a different input feature. So the decision trees itself are not going to be the same. So it's definitely a little bit harder to visualize and interpret, especially on a larger scale. Okay, so that's random forest models or random forest classifiers. And so the takeaway I want you to understand from that is that it really just behaves like a group of decision trees, right? For a decision tree is made for each feature or input, right? And then we take that feature or input decision tree, we get the output from that, and then we see which output or class is the most common across all of our decision trees for all of our input features. So there you go. That's random forest models. And now let's talk about k-nearest neighbors, which is more of a clustering technique in supervised learning. And it's pretty similar to some of the unsupervised learning techniques, like k-means clustering. But for our purposes, we're only talking about supervised learning right now. We'll get to unsupervised learning later in another video. But for now, we're sticking with supervised learning-based k-nearest neighbors models. And this is used for classification, typically, sometimes for regression, but 80% of scenarios, classification. So let's talk about how this algorithm works. What is the k-nearest neighbors algorithm? So this algorithm is built on one very important assumption. Without this assumption, you can't really integrate with k-nearest neighbors models. The assumption is that similar data points will exist near each other graphically. Well, let's break that down. What does this mean? We're assuming that the behavior of certain data points or examples, in other words, their labels, it correlates with their location on the graph. In other words, data points that are very similar will lie very near each other on a graph. That's all it is. That's all it means. It's just basically saying that we're assuming that, like in real life, since these data points are really similar in behavior and the way they interact, they should naturally also lie near each other on the graph, graphically. And that's what k-nearest neighbors is all about. It captures this idea of similarity, right? We're always looking for the distance, proximity, or closeness of different data points. So k-nearest neighbors, when you use it graphically, which it usually is used for, it's all about how close the data points are near to each other. Are they clustered closely? What's the distance between them? What's the proximity, the closeness, etc.? And the main assumption here is that we assume that data points with similar labels and behavior will exist near each other on graphs. So there you go. That's the assumption for k-nearest neighbors. But how does the actual algorithm work? How do we construct a k-nearest neighbors classifier? So this is a very simplified version. This is not how it obviously works for when you actually want to implement it in code. This is kind of the very, very high-level pseudocode for implementing or constructing a k-nearest neighbors classifier. Step one will be that you calculate the distance. So what you're going to do is that you're basically, when you calculate the distance, you're going to look at all your training examples, and you're going to look at the examples that are most nearest to the one that you've selected. So in other words, you take a new example you want to classify. You have some initial example that you want to look at. You then take that example, you look at all the surrounding neighbors, and you calculate the distance to each of those neighbors. You find the few of the neighbors that are the closest, right? So it's kind of hard to see, but you see in the graph that says calculate distance, you see that we have some new data points, some new initial data we want to classify. We look at all of its neighbors. So you see there's 3 stars that are neighbors and 3 triangles that are neighbors. So there you go. There's 3 class A's, 3 class B's. And then we vote for neighbors. So we have a range of the 3 closest neighbors, and we vote. So it's a little bit hard to see, but as you can see, we have our value of k being 3. K equals 3. In other words, we're picking our 3 closest neighbors, and that scenario, you see there's 2 class B data points, or 2 class B neighbors, and there's 1 class A neighbor. So there you go. For our 3 nearest neighbors, we basically do a vote for which label is more common. Is class B more common or class A more common? Right? And you may be thinking, what happens if there's a tie, right? Let's just say we did k equals 4, and it gave us that there's 2 class A's, 2 class B. Then in the case of a tie, then you have to increase your value of k, right? You have to look at the next closest nearest neighbor, right? That's how it works. And so this is actually, it's a pretty simple process, right? When you think of it at a high level. But in reality, when you implement in code, it's not that simple, right? But I get the idea here is that I want you to understand is that if we have a new example you want to classify, we know its position, we calculate the distance to all the nearest neighbors, and then depending on our value of k, let's just say in this case, right, k was 3, then we look at those closest neighbors inside our little range of k, like for the 3 closest ones, and then based on that we vote for the neighbors based on the label, right? Let's just say we had a range of k equals 5, we had 3 class B's, 2 class A neighbors. In that case, class B still wins, 3 over 2, and there you go. The final output will be class B is the most likely label for this example. So there you go. That's how k-nearest neighbors works. So it's a very arbitrary process when it comes to how to choose your value of k. So just to reiterate, k is the number of neighbors you want to explore within your little bubble, right? So going back here, so we picked k equals 3. So this is arbitrary, right? You really want to pick k in order to minimize your error and your validation error. But I think in this case, they just pick k equals 3 for simplification purposes. But as you can see, when we pick k equals 3, that means that we're exploring 3 neighbors that are closest to us. So in other words, k is the number of neighbors that are closest to the example we want to identify. So k, in other words, is the n number of data points that lie as close as possible to our training example, or the example we want to classify. And so when we actually want to choose k, when we're implementing this algorithm, it's kind of a trial and error process to choose it. You want to both have a lower error rate and a lower validation error. And so here's an example. So there's 4 graphs on this slide. You see there's 4 different iterations. We tried a graph of when k is equal to 1. We have a graph when k equals 3, k equals 5, k equals 7. And in each of these, you see how we pick a data point, and then we explore all of those k nearest examples, and then we classify it. And then that creates what we call a boundary, right? Like a decision boundary when we go back to SVMs, right? And so there you go. So that's how the separation is made. And the idea is that we will look at all these graphs for different values of k and see which one gives us the lowest training error, the best scenario for our validation error and our training error. Let me re-explain. So the idea of picking our k is all about balancing error, right? So we test different values of k using trial and error, right? We pick different values of k. We want to see how it works. And then the idea is that we can look at both our training error, or our error rate, and our validation error. So let's look at both of them. So here's the graph for as k increases, how error and validation error increase, or decrease. And as you can see, at low values of k on our validation graph, you see that we're overfitting. In other words, our validation error is really big, because that's bad, right? When k is really small, you're only checking the neighbor right next to you, right? In some cases, that model might work great, but in other cases, for test data, for completely never before seen data, that might be terrible, right? Because we might just not want to see the only one neighbor near us. We might want to explore way more. So that's why at low values of k, for a validation error, our validation error is extremely high, and we're overfitting, because it's not enough to just check one neighbor, because sometimes that might work great, right? That's why you see on the error graph, for when we only check one neighbor, it's basically perfect, right? Zero error. But for a validation error, it's not good, because checking one neighbor is not enough, right? For completely never before seen data. And there you go. So in other words, what I'm trying to get you to understand is that looking at just simply the error for training is not enough, right? I think it obviously is common sense that as you increase the number of Ks in your training data, it will make sense that the error will also increase, right? But then for validation error data, you want to find the optimal K in that data. Because validation error is really the real world performance of your classifier, of your K nearest neighbors classifier, right? So if you look at this validation error graph, then you're probably going to see that the validation error hits a local minimum, or the absolute minimum, at about k equals 10. So there you go. That's the optimal k. Because at that k, we're not really overfitting or underfitting, right? We have a k that allows us to explore enough neighbors to actually get a good sense of our classifier, right? To get a good sense of what we want to classify as. But at the same time, we're not looking at so many neighbors that we're inefficient, we're causing more error, we're maybe underfitting, etc. So there you go. That's how we find the most optimal K. So the takeaway here is that we do trial and error across different iterations of K. So we'll look at K equals 1, K equals 2, K equals 3, etc. And then based on that, we'll basically look at these curves for error and validation error to find out where we want to find that optimal K. So this is actually like really similar to tuning, but it's not quite tuning, right? Because you initialize K at the very, very beginning of your K nearest neighbors model, right? You're not going to initialize K at the end. K is the fundamental parameter in this model when you're implementing it. So you initialize K in the beginning, right? And it's really about just trying different values of K, right? To find out which works best. So there you go. And the way we do that is we look at the validation error graph. What are some of the advantages of a K nearest neighbors classification model? It's very simple and easy to implement. So I'm going to show you some coding examples later in this video, but I think with sci-kit learn and a lot of different libraries and frameworks, it's actually really easy to implement this model. And in general, if you coded it from scratch, I guess, it's also pretty easy to implement. Because remember, it's some basic mathematical formulas and principles. You're calculating the distance, or the Euclidean distance, from the data point you want to explore to all the other data points. And then, based on that, based on your value of k, you search a certain number of neighbors, right? So I think on this slide, it has a graph. So you have that yellow dot in the middle, that's the data point that we want to classify. We explore those 3 examples, because maybe our value of k is equal to 3 in this instance. And then you basically calculate the distance to all those examples. We find the 3 closest ones, since our k is equal to 3. And then boom, we see whether the red label or the blue label is more common. And in this case, I think it's the red label, 2 versus 1. So that's how we would classify that yellow data point as red. Makes sense. Another advantage of the k nearest neighbors model is that there's no need to tune it or make extra assumptions. Our fundamental assumption, going back to this slide, is that similar data points will naturally exist near each other graphically. In other words, we're assuming that data points with similar behavior and similar optimal output will be very close to each other in proximity or closeness. So there you go. We don't have to make any other assumptions. That's the main assumption we're making. And there's no need to tune this model, because in terms of if you're thinking of what's the loss function, or how's this going to work for increasing accuracy, then there's no need to run optimization on this model, because naturally that all depends on your value of k. K is the major parameter here, and when you initialize k, that's a tuning process in itself. So there's no need to do extra tuning to minimize some loss function. There's no need for that. Also, k nearest neighbors is a very versatile algorithm. It has multiple applications. In fact, it's also used for regression in some cases, but it's usually used for classification. But in general, it's a very versatile algorithm, even useful for searching or clustering. What are some of the disadvantages of k nearest neighbors? It's that it doesn't scale well. Similar to random forest models, I think these 2 types of models have issues when it comes to scaling with a lot more data, right? In other words, it's inefficient for a large number of training examples. Another disadvantage, similar to the random forest model, is that it's difficult to visualize for a large amount of data. And unlike the random forest model, I think k nearest neighbors has one bigger problem in that depending on your value of k, you can have a lot of overfitting, right? So that's why it's very crucial to spend time and really pick that correct value of k based on the validation error. Because if your K is off, then you can face a lot of overfitting. In other words, maybe on the training data, you're doing awesome, right? But then on testing data or validation data, your error is a lot. You're inaccurate, you're not making correct classifications, right? So that's bad. And that's why it all depends on K. And this model is more easy to overfit, right? Because you can just pick some random K, and there you go. You maybe picked a K that wasn't optimal, and your model overfit to the data. So that's not good, right? So that's why picking K is essential. It's crucial to the model. Picking a good K is very important. So there you go. That's the disadvantages of K nearest neighbors. I'm not going to do a full coding tutorial in this video, but I do want to take a second to just quickly go over the coding implementation, or how you maybe really quickly would try to implement this code for both random forest and K nearest neighbors in scikit-learn. Here's the implementation for a random forest model, and this is a really small sample of code, right? This is definitely not the full implementation, and this is all using scikit-learn, right? It's definitely possible to do a raw or from scratch implementation of a random forest model, assuming you have data and you have all the mathematical functions. But I think it's easier to use scikit-learn since it's a framework that already has inbuilt classifiers. And here you go. It's just, I think, going back to the very first time we did like a coding example, I think it's all about like how scikit-learn is a really easy to use framework, right? Scikit-learn will give you functions, will give you classes where you can just basically just fit some data to that class, right? It makes your life way easier. So in this case, you see that from scikit-learn.ensemble, we import literally random forest classifier for random forest model. And then you can basically just create the Gaussian classifier. You can train your model with your X train and your Y train. And then boom, you can just do sample predictions. So there you go. That's how it works for random forest. Similarly, K nearest neighbors is also built on scikit-learn in that there's already a pre-made framework for that K neighbors classifier. And yeah, it's really simple implemented as well. So the code is here. So you just say model, you initialize your model as model equals K neighbors classifier, and then in the parentheses for this class, you're basically just going to set your function or your number of neighbors to some arbitrary value, right? And by arbitrary, I mean like you initially start with some arbitrary value because you want to initially just test it, right? You want to test for which Ks are better, which Ks give me more accuracy, less accuracy, etc. And it takes some time, right, to look through both the validation data and the error rate. So that's how it works. And then, as simple as it can be, you just say model.fit to features and label. And boom, that's how simple it is. There you go. Let's finish off this lecture. Let's talk about some of the takeaways from today's video. So I think we've understood both K nearest neighbors and random forest models, and I think it's overall they're both really useful techniques of supervised learning for classification. Both can also be used for regression, but I think they're typically used for classification. K nearest neighbors uses clusters, the idea of distance or proximity as the main assumption, similar to clustering. It also works as a lazy learner, right? And on the other side, I think the best way to remember what random forest models are and how to implement them is just that it's a collection of decision trees, where each decision tree is based on a certain input or feature, and then for each input feature you have a decision tree, right? And then each decision tree will give you an output or some label, and you see what's the most commonly occurring label after all the decision trees give you some output. Basically the mode, right? The most commonly occurring value of labels. And that's your final prediction. So both are pretty easy to understand, right? I think K nearest neighbors is a natural idea runs on the natural assumption that data points that are supposed to be similar in behavior will naturally be closer to each other. And random forest models is just a bunch of decision trees, right? Like the same way in real life, a forest is a lot of trees, a random forest model is a lot of decision trees, right? I think that's pretty cool. And both are usually typically highly accurate and robust, but I think the drawback is that they don't scale well to large amounts of data, and that's an issue, right? All right, and that's it for today's video. I hope you guys enjoyed the video. Thank you for watching. Make sure you hit the like button and make sure to subscribe. And I will see you next time for the 9th video in the series. And so once again, thank you for watching. This was the 8th video in the series. I will see you next time. Thank you and goodbye.